The ability to detect visual targets in noise is key for interacting with the environment. For example, recognizing a predator in the wild or a fast-moving moped when crossing a busy street. Learning to detect targets in noise is underpinned by plasticity in visual brain regions. This includes changes in the inhibitory neurotransmitter GABA and in functional connectivity between visual brain regions. However, recent work on experience-dependent changes in myelin, a phospholipid sheath that wraps around neuronal axon segments, suggests myelination is also an important mechanism for learning-dependent plasticity. Here, we take advantage of recent advances in MRI indicators of myelination to investigate myelin plasticity following visual learning and its relationship with GABAergic plasticity and functional connectivity. First, we trained participants on a signal and noise learning task in which they detected radial or concentric patterns from visual noise. We conducted MRI imaging at baseline, in a pre-training session and after training. We found a significant increase in MT, an MRI indicator of myelin, after training, in a subcortical cluster containing thalamic regions. MT change in the right pulvinar was also negatively correlated with behavioral improvement. This suggests learning-dependent pulvinar myelination relates to perceptual learning. Consistent with previous reports, we also found a significant negative relationship between behavioral improvement and GABA in the visual cortex. And interestingly, we found that changes in pulvinar to visual cortex connectivity were negatively related to behavioral improvement, but positively related with visual cortex GABA and increased pulvinar MT. This suggests an important role for thalamocortical connectivity in learning-dependent GABAergic plasticity in visual cortex. Together, our findings suggest attentional thalamic mechanisms may interact with inhibitory processing in visual areas for improved perceptual judgments after training.